Hello, I'm Wasim Ali, and I'll be going over an overview of my CubeSat internship during the spring of 24 semester. At the start of my internship, I was given the objective to see what I could do with the Pumpkin Development Board, which is a laboratory platform for CubeSat kit training, development, debugging, and testing with an attachable pluggable socketed processor module E or PSPME, which is built with a PIC24FJ256 GB210 processor in mind, which is what I was targeting for the first part of my internship in terms of programming it with an RTOS or a real-time operating system, which guarantees real-time applications a certain capability to meet deadlines. This is often used for time-critical scheduling, such as with pacemakers and such, where a program meeting a schedule every time is crucial. For RTOS, I was pointed in the direction of Salvo, which, like the Pumpkin Development Board, was also created by Pumpkin, claims to be designed for very low-cost embedded systems with limited program and data memory, and also promised to be very easy to use, highly configurable, and scalable. In terms of development environment, I was pointed in the direction of the MPLab IDE, our integrated development environment. On the MPLab site, it claims to be an expandable, highly configurable software program that incorporates powerful tools to help the programmer discover, configure, develop, debug, and qualify embedded designs for most of our microcontrollers and digital signal controllers. Some features which make it unique among IDEs are a data visualizer, which displays real-time streaming data, and an I/O view, which personally I found very helpful when getting it set up for a basic LED Hello World application, which I will cover in a bit. One thing that I found very noteworthy is the sheer size of the installed application, as it took up over 10 gigabytes of space. The additional toolchain downloads that were necessary to target the PIC24 processor on the development board alone took up several gigabytes of space as well. The first real task was to perform a smoke test on the development board with Professor Marshall's help, which essentially means seeing if we can get the board powered up without smoke coming out. After looking over the jumpers, Professor Marshall decided to try to power on the board through the USB connector J4 on the processor module. No smoke came out, and the VCC light on the development board turned green. The PIC Kit 4 debugger, pictured here, was plugged into the processor module. We looked over the jumpers, decided on trying to power the board through USB connector J4 on the processor module, and found that no smoke came out, and the VCC light only on the development board turned green. The PIC Kit 4 is plugged into the processor module via ICSP and was powered up through my laptop, but the board lost power, lost VCC. In the end, we powered it up using both of our laptops, and I got MPLab running on my machine to recognize the board. Professor Marshall used DuPont jumper wires to hook the anode of a red LED to H2.24 and the cathode to a 10K resistor, which then goes to H2.30 DGND. This left me with the task of working out MPLab X's pin mapping function to blink the LED as a hardware hello world. The next morning, I was able to turn on the LED with the help of a Blink application lab available on the Microchip website. It wasn't working at first, but after going through all of the header files and adjusting the pinout to the way we had the LED set up on our board, the light came on. For the next couple of weeks, I spent a lot of time trying to get many different Salvo demo applications to work with no success. I found that a lot of important files were missing from the Salvo Lite download, and the MPLab IDE reflected in the documentation is entirely different from the one available today. For these reasons, I decided to try out FreeRTOS. FreeRTOS promises to be the easiest to use. It had been a couple of weeks working with the demo configured for a PIC24, albeit not the exact PIC24 I was working with, but something similar. This demo needed a C30 compiler to run. I always got the error you see here when trying to build. I checked the make files. I checked that the make files were there. I hadn't changed a thing, but I was still getting no success. It was very discouraging that I was running into problems running the demos right out of the starting gate. As I was not having much luck running the FreeRTOS demo on the MPLab IDE, Professor Marshall suggested I try my luck getting an ESP32 to run FreeRTOS through the ESPIDF, which was the new development environment. According to the Espressive site, ESPIDF is Espressive's official IoT development framework, which is geared towards several versions of the ESP32. It claims to provide a self-sufficient SDK for any generic application development using programming languages such as C and C++. It can program various devices from simple light bulbs and toys to big appliances and industrial devices. The setup and installation phase to get everything ready to go was very long and not very straightforward, but I found that Espressive provides access to excellent, up-to-date, step-by-step documentation to help users navigate their way through it. Professor Marshall pointed me to the ESP32 you see here to target. Once everything was set up, I successfully was able to get both Hello World and Blink demos to work targeting this board with absolutely no trouble. I documented all my resources, which helped me get everything up and running in the spring 2024 CubeSat log for future reference. Finally, I was successfully um, able to get a reading from a piece of hardware to read input using a real-time operating system, which is something that would be useful and which we now know is one of the viable options as a launchpad to work on during uh, building up to APU's first CubeSat mission. I was very grateful for the opportunity to work on APU's CubeSat program. The advice I would give to future lab technicians is not to be daunted when faced with assignments that can be somewhat more complex or challenging than your typical programming assignment. And if you're a computer science student, you may be surprised to learn that working with hardware can be quite fun. Failures come with the territory and they just mean you've found ways that don't work and are still useful discoveries nonetheless. Finally, don't be afraid to ask for help as there are excellent faculty, staff, and student resources available at your disposal. This concludes my presentation. Thank you very much.